Hi, everyone. I want to welcome you to the CUNY Graduate School Public Health and Health Policy Grand Rounds. I'm Elizabeth Kelvin, and I'm an associate professor and the chair of the Department of Epidemiology and Biostatistics. And I am very pleased to introduce our speaker today. Andrew Gelman is a professor of statistics and political science at Columbia University. Sorry, I'm having a little technical difficulty here, which might be why I'm dinging. Let's see. Sorry, one sec. All right. So Andrew Gelman is a professor of statistics and political science at Columbia University. He has conducted research on a number of topics that are particularly relevant in the current political climate, including why it is rational to vote, why campaign polls are so variable when elections are so predictable, and why redistricting is good for democracy. He's also conducted research on important areas of public health, such as arsenic in Bangladesh and radon in your basement. And of course, he's conducted research and written on statistical challenges, such as the estimation of small effects. He's received numerous awards, including the Outstanding Statistical Application Award from the American Statistical Association, which he won not once, not twice, but 3 times, and the Council of Presidents of Statistical Societies Award for Outstanding Contributions by a person under age 40. Today, Dr. Gelman will talk about generalizing from available data to a population of interest, which is, of course, one of the fundamental goals of epidemiologic research. And so let's give a warm CUNY School of Public Health welcome to Dr. Gelman.
Well, thank you. It's a pleasure to speak at CUNY, and I mean, it's a real honor. My grandmother went to Hunter College, and my father went to City College, and my wife teaches at Hunter College. So I have a lot of love and respect for the institution. I just wanted to say one thing before starting the talk, which was that you mentioned my paper on redistricting being good for democracy. I don't think redistricting has been so good for democracy lately. We published that paper in 1994, and we studied state legislative redistrictings during the could someone, excuse me, but could one of the people involved who invited me, show your face? Because it's much easier for me to give a talk if I can see people. Thank you very much. So we studied the effects of state legislative redistricting in the 1970s and 1980s. And what we found, there were 2 worries about redistricting that we addressed in our paper. And one worry was that redistricting would be used by incumbents to protect their own districts, making it hard for new people to enter politics. The other concern was that partisans could redistrict and gerrymander in order to get unfair advantages. What we found in our statistical analysis was that first, redistricting did not reduce the competitiveness of elections. It made elections more competitive. And the reason for that was that in the absence of redistricting, at the time, there was a large incumbency advantage. And in the absence of redistricting, incumbents would just sort of stay there because of the legal restriction that when you redistrict, the districts have to be of equal population, that required the districts to be shaken up. So it just put in some shifting in the system, which was good for new entrants. The second concern was that redistricting would benefit parties. We found empirically that the benefit for the party who controlled redistricting was about 1% of seats in the legislature. Well, 1% is not nothing, but it's not huge. Why is that? Because redistrictors were under a lot of constraints back then. There was a fear of judicial review. And so the extreme gerrymanders didn't even get proposed. Now, what's happened since 1994 when we published our paper? I mean, we did our research around 1990, but our paper is published in 94. between then and now, first, technology has changed. So you can draw much more, there's a lot more political data available, which like I'm partly to blame for. And it's easier to gerrymander. The politicians know where everybody lives, and so they can draw these very elaborate maps that have the right population, but manage to get what they want. The second thing is that the advantage of incumbency has lowered. The third is that the political climate has changed. Because of increased polarization, parties can kind of get away with more. It's possible for parties to do very partisan things. And in the past, they wouldn't want to lose the moderate voter, but that's kind of less of concern now. And finally, the climate of the courts has changed. So putting all that together, now redistricting is now, I'm not sure. I'd like to say from reading the newspapers, it can do a lot of bad things, but I don't really know. I think more research is needed, but I just felt bad when you said that, like, I wrote a paper on redistricting is good for democracy. I feel bad about writing that paper. I mean, because, and this relates to the talk today. Okay, so yeah, I shouldn't have written that paper. Like I did like my part to make the world worse because people were concerned about gerrymandering, and we were like, no, chill out. Galaxy Brain says gerrymandering's, not a problem, right? Like it's just you guys don't understand, right? If you look at it carefully, well, I think we were right, but on the other hand, redistricting, you could say the American redistricting system was a ticking time bomb because the ability to gerrymander was always there. It was only held back by various political and legal constraints, which were not apparently so permanent. And that was so, what did we do wrong? We estimated the causal effect at what happened, the causal effect, the average causal effect integrated over 30 states. Well, there's data reasons why we only had 30 states. Don't worry about that, but integrated over 30 states over 2 decades. And our estimate was this is the effects of redistricting. We did some pretty nice causal inference. There's actually some cool stuff we did. When you look at, we basically ran a regression. We did a lot of analysis for every state legislature in our data set. And every election year, we came up with a measure of partisan bias and a measure of electoral responsiveness. And what we found when we analyzed partisan bias was not only that the effect was not that large, so being a Democrat or being a Republican and controlling redistricting didn't have that big an effect. It turned out that the biggest effect of redistricting on partisan bias was to send it towards zero. So if you want to talk statistical jargon, there is an interaction between when you predict, if you predict next year's partisan bias based on the last year's partisan bias, and the treated states are the ones with redistricting, and the control states are the ones without, the slope for the control is very high because, am I supposed to draw it like this because I'm all flipped? Yeah, okay. The slope for the control is very high, close to 1, because if there's no redistricting, if there's no redistricting, then the partisan bias next election will be similar to last election. It only changes because some voters shift and so forth. When there is redistricting, the slope was much more like this. There was some correlation, but it was much lower. So the biggest effect was actually the interaction. The interaction was, in that case, more important than the main effect. Well, that's all fine. The funny thing is, though, like it took us, we only did that because we thought of doing that. I mean, what I mean is like you estimate the causal effect, you run a regression, it's an average causal effect. What's the problem? Well, the problem is there, what I told you. So, but if you look at the textbooks, they're always like average causal effect, main effect. Oh yeah, you could look at interactions. Okay, I'll get back to that point. Okay, but yeah, like, okay, why is it the default, like there's a main effect but no interaction? Well, that makes sense. When I was in college or graduate school, I learned statistics. They told us that like naive people think about treatment and control, but the sophisticates think they're just 2 different treatments, right? There's no such thing as a control. The control is what you're comparing to. Well, kind of, but no, there is a difference between treatment and control because the treatment's when you do something. So it makes sense, right? That if you have a before measurement and after measurement, the correlation between before and after will be higher for the control group than for the treatment group. Just by default, our default model shouldn't be that the lines are parallel because it makes sense that that the treatment does something. Now, a treatment can cause inequality in a sense. Like you can have a treatment which makes the rich richer and the poor poorer. You can have a treatment like redistricting used to be back in the day that caused equality, that after redistricting, things were less. Or all other things are possible, but it makes sense to think of no change as the default. Why don't we think about that? I think it's that the way we teach and think about causal inference is wrong. Is fundamentally wrong. It's kind of my fault too, like as a textbook writer. So when I was a student, I learned about this fundamental problem of causal inference, this idea that you can do the one treatment or the other, but not both, right? So you can never estimate the individual treatment effect, but if you have a randomized experiment, you can estimate the average treatment effect. And so that's what we do. But so the paradigm is you have two treatments and an outcome. If you look at like the textbook and then maybe you'll have other predictors. Okay, I think that's wrong. I think our baseline paradigm should be you have a pretest measurement, a treatment, and an outcome. Well, you don't always have a pretest measurement. That's too bad. It's like, then you have to consider it as latent, but you should imagine it's there. Like, well, there are situations where there's no pretest and there's not even a conceptual pretest. I mean, like the baby is born, there's no pretest like measurement, but we had an example like that recently. But typically there is either a pretest that's measured or that could have been measured. And then there's this baseline, which is nothing happens. Well, under the control, something will happen. Like, kids get bigger, people, young kids get bigger, old people get sicker, like things happen. But like, that's a change. That's kind of important too. So I feel like we should really be embedding everything in these kind of time series perspectives. And I'm still working on it. Like I would say there's a paper to be written on just the framework of this, like how to think about everything. Then all the other things we do are special cases of this. But out of this kind of time series framework, you'd automatically get this interaction because it's like regression to the mean kind of thing. It just pops out. You don't have to put it in. But because we have our theoretical framework is so lacking, we don't have that. And it's a problem, and it's a kind of pseudo sophistication, which maybe that's the theme so far of today's talk. I was pseudo sophisticated before. There is a pseudo sophistication where it's like treatment control. What could be simpler than that? Like, why muddy the waters with a pre-treatment measurement? That's optional. Well, maybe not. Like, yeah, in practice it can be optional, but maybe it shouldn't be thought of that way. So to get back to the main theme of this talk about modeling and post-stratification for descriptive and causal inference, we got causal inference for what happened in the 70s and 80s, but there's no reason to assume that would be true. So how do you generalize? As of 1994, how should we have generalized from the 70s and 80s? We should have said, this is what we found. We didn't say anything false. Like we said, this is what we found, but we probably should have said, if you're reading this paper, you might care about the future. And in the future, these are the conditions under which we would expect redistricting to continue to be good for democracy. Under these other conditions, we're not sure, right? We should be really integrating our statistical analysis with the theory. And even at the end, like even at we call story time, right? The part of the paper after you got your result, and even like I had a colleague once who told me a very smart piece of advice. He said, putting your best stuff after the paper's been accepted. After it's been accepted for the journal, you can do one little change and then you can put in whatever you want. They're never going to look at, right? So like, and there's a lot of places where you could talk about this stuff. And I think usually in story time, we're spending most of our time like just justifying our results and covering our butt and saying we didn't do anything wrong. But there it's in retrospect, well, 1994, I don't know. Well, this was like, we wrote it more like in 92, right? So should we have, I don't think that political polarization seemed like such a big deal. looking back on our political science work, 1992 was arguably the first of the modern politically polarized elections. But at the time, it was like Bill Clinton, George Bush, whatever. These were like, I think in retrospect, Clinton seems like a moderate and so does Bush. But at the time, it seemed like a typical, Democrat on the left, Republican on the right. People are deciding how to vote. We didn't know we were entering some new phase of politics. So it's not that we could have anticipated that, but we could have thought about the conditions, and we didn't do that. So I really fell down on the job. I would say my colleague and I could have done better. So I apologize for that. So I want to tell you, we start out in Regression and Other Stories, we talk about the three challenges of statistics: generalizing from sample to population, generalizing from treatment to control group, and generalizing from observed data to underlying constructs of interest. And in applied statistics, these are usually thought of as three different things. The first is sampling, the second is causal inference, and the third is measurement. And I think that all three are important for just about every problem. Well, causal inference, I'm not sure. I do a lot of straight descriptive stuff. I like to say that there's a division of labor. And the division of labor is I'll describe what's happening and somebody else can describe like what's causing why. Because if you notice, like a lot of social and health sciences involves people trying to come up with explanations for things that aren't true. So I think it's actually great if we can contribute just by trying to nail down what we really know about the world. It's subtle, right? Like this is like old-time philosophers used to talk about. The role of the statistician is not to discover the truth. The role of the statistician is to discover what the data tell us, right? And this often happens. I'll criticize some paper and say, I don't believe it. That doesn't mean I think their claim is false. It means that I don't think that their claim is supported by their data. But sometimes I do care about causal inference. And the theme of this talk is how issues of sampling come up in those settings. But what I'll do is I'll first give you a couple of straight up sampling examples, or maybe I'll give you one sampling example just to get started, and then we'll talk about some of the causal questions. But before I start my talk, I just wanted to share something with you, because this year I've been teaching out of Regression and Other Stories, and I decided I want to teach like the way I wanted. I want to teach with student involvement. So every class period starts with a story, and then we have a class participation activity, then we have a computer demo, then we have discussion, we have drills. It's not like this talk, like this, I'm just talking at you. It's horrible, right? I'm just yapping and doing this, right? In my class, I'm not doing that. It's all the time we're stopping students, having them work in pairs. Anyway, to create this class is 2 semesters. It's 13 weeks. Meets twice a week, right? Because you should never have a class that meets once a week. That's horrible. I really wish they could meet 3 times a week, but no, they don't do that anymore. So twice a week. So that means I need 52 stories. I need 52 class participation activities. Okay, I have 52 stories, but they have to be connected. So every time we tell the story, I stop at the end and say, the relevance of this story to this week's readings is blah, blah, blah. The relevance to the course as a whole is blah, blah, blah. I have to have that rubber band connecting the story back to the course. So I used to just tell stories, and it's like, that's fun, but you're not learning the material, right? So that's why these stories all connect to this theme of modeling and post-stratification, which we'll talk about. Anyway, I also had to come up with 52 class participation activities. That's hard. I wrote this book with Deb Nolan, The Bag of Tricks for Teaching Statistics. So I thought, well, it's a big book. We don't have 52 class participation activities. With like 6 or something. Like we have very few. So this has been a lot of work, but it's really been fun, and I wanted to share one with you. So just for fun. So there's a game that the kids sometimes play called 2 Truths and a Lie. So maybe you've heard about this. So the game is that you say three things, and the other person has to guess which of those three things is a lie, right? Two truths and a lie. So it's so much fun. I wanted to have an activity around it. And then I was going through the semester and we're teaching logistic regression, and I thought this will be perfect. So I'll show you what we do. So I'll share the screen just because it's fun. It's nothing to do with the class. I mean, you're nothing to do with this thing, but it's fun. Okay, so I put this up on the screen for the students. So the students have to divide in groups into groups of 4. And then one of the students is the storyteller, and he or she has to tell 3 personal statements. Then the other 3 students in the group, so students are clustered in groups of 4 now, right? The other 3 students in the group confer and decide which they think is the lie. Then they also give a certainty statement, which is 0, I have no idea. We have no idea. 10, we're certain that this person, we figured out the lie, right? Then the storyteller reveals which was the lie, so that 3 students know whether they got it right or not. And then they enter their certainty, they write down their certainty estimate and the outcome. So, oh, and then they rotate. So there's 4 students, so each one gets to be the storyteller. Doesn't take long, right, to come up, especially if you know you're going to be doing it. So then each group will have 4 data points, like their certainty and whether they're a success. Then we create a Google form. Okay, we create this little Google form. It's really easy to create a Google form. And they just, well, I set it up so that you just have one response. So you just have to go into the Google form, enter your certainty and the guess, and then each group just does it 4 times. Then we have the data, right? We have survey responses. Well, you can look at the distribution of certainty statements. That's kind of silly, but you can download the responses as a CSV and analyze them in R right then in class. Right then you can analyze their data. We found that the certainty statement, the certainty score was just not a good predictor of whether people are correct. We did logistic regression. Is your guess correct given the certainty score? And before I did the logistic regression, this is also something you should do. Before we did the logistic regression, I had them go into pairs and say, what do you think the logistic regression is going to look like? So we draw the axis. The x-axis is probability of successful guess. The y-axis is probably a successful guess from 0 to 1. The x-axis is certainty score from 0 to 10. I say we're going to have 50 data points, and we're going to run logistic regression. And what do you think the estimated intercept and slope is going to be? How do you figure that out? The intercept, well, where does it cross 0.5? So they made their guesses, but the slope was basically 0. Was kind of interesting. Only because I told myself I need an activity for every class. I'm no longer going to show up to class and just wing it. I'm just all prepared. And so we do that. So we're going to have, this will be a book, right? A free book for people. So anyone can teach like this. I don't think everyone wants to use all my activities, so people can do their own, but this would be a model. So I think that would be wonderful. Not the topic of today's class at all. In fact, today's lecture, in fact, pretty irrelevant, because I think I've heard that the School of Public Health, they don't teach a lot of classes. At least at Columbia, they do very little teaching in the School of Public Health, because they do a lot more research. We're at the college, so we do more teaching and less research. It's a balance that way. Okay, so let me tell you first about modeling and post-stratification for descriptive inference. And I think I could talk about survey statistics we do, we do a survey and it gets too many women and not enough men. And so people say, oh, you have to weight the women down and the men up, and you have this and that. Weighting, I don't think survey weighting is a good paradigm for analysis of survey data, even though that's how everybody talks. And one way of seeing this is the weighting just doesn't get you out of the people in your sample. So for example, if I do a survey, a national survey, and I get 12 respondents from Vermont, and 10 out of 12 happen to say that they support a certain policy, then no matter what weighting I'm going to get, I'm going to, or if I want to even be more extreme, I have 4 respondents from Vermont, and all 4 respond yes to the survey question. Doesn't matter what weighting I do. It's all the average of 4 yeses is going to be a yes, even though I know that's not going to be the case. So like instead of thinking of the survey problems, the sample's not representative of the population, instead of thinking of it as a weighting problem, a problem to be solved by taking the data and adjusting the data, we think of it as an inference problem that I'm trying to learn about all the people in the population who I haven't sampled. So it's like kind of an obvious idea. Well, what's its implications? So I'll talk to you about some surveys, not political polls, where this came up. So the first example was from about 20 years ago at the School of Social Work at Columbia, where a colleague was doing a study of urban American Indians, actually American Indians in New York City. And this was not a, yeah, I mean, this was that she wanted to do, ideally she would have had a random sample of New York City resident American Indians. There was no sampling frame that you could do that from. Not everybody is registered with a tribe, and you don't have everyone's like address in any case. So what she did was she started with a community organization, and she got 100 people from the community organization, and then she did referral or network sampling, where the people in the organization then recommended new people to be contacted, and she did several waves of that. I was involved in the design of the study. I don't actually know what happened. Now there are some obvious concerns in this study, obvious sources of bias. So 3 sources of bias. So the first source of bias is that you're starting at an intake point, and this is members of an American Indian community organization. And so since you're starting at this intake point, people who know somebody that way are going to be close to that. So you're going to get somehow maybe people who are more Indian identified, partly from the initial where it started, but also because they asked people, can you refer me to someone who's American Indian? So like, what if they know someone and they don't even realize that they're part of a tribe? So that's the first bias. The second bias is that you are more likely, well, actually, those are 2 biases. One is connection to the intake point. The second is the identification issue. The third bias is that you're more likely to get gregarious people, right? Like if you're a hermit, no one's going to recommend you to be in the survey in the first place. So you're going to oversample popular people. And so this is really not a survey of New York City American Indians. It's a survey of strongly Indian identified New York City American Indians who are close to somebody who's part of this organization and are popular. And that's so how do you deal with this? There's some theory, probability sampling. What's the probability that you're going to be selected? How do you, I don't think that's the right way of doing it. I think the right way of handling this problem, the sampling problem, is very direct. And the direct thing is to say, I think the sample is non-representative on these characteristics. So I am going to try to measure these characteristics on each respondent and then try to adjust to match what I know about the population. So Indian identified, you should ask people in the survey, how strongly do you consider yourself Indian identified? I don't know how to ask the question, but the point is you can do that. You can measure that on each wave. And well, you don't know that for the population. So any post-stratification you do will be speculative. Still, it's better than not doing it. Then you'd say, well, under this model of the distribution of Indian identification in the population that we care about, this is what will happen. Similarly with gregariousness, well, you can ask people, how many people do you know, or things like that, or even how many people do you know in the American Indian community, right? You can ask that, and then you can adjust for it. Again, you don't know it in the population. You can kind of estimate it from the sample, but the fact that your estimate might be wrong is no reason not to try to adjust at all. because you know there's a bias. And closeness to the intake point, in this case, maybe it's captured by this other thing. So we had a similar issue with a survey that was done in another country. It was, and I don't remember where, some political science students were working on this. This was about 10 years ago. They went to a city where there was some tumult, and they wanted to do a survey and ask people about their participation in protests. But they didn't have a sampling frame. They couldn't call people at random or go to people's addresses at random. So they just went to a few places in the city and like set up a table and started interviewing people. Well, how is this going to be biased? Well, you're going to be biased towards people who are friendly enough to come to the table. You're going to be biased against whatever demographics you have, obviously location, whether people work in the area. So again, the point is you measure that. You ask people where they live and where they work, and then to the extent it doesn't look like what you think the population of the city looks like, then you do some post-stratification, do some adjustment. So it can be done. And I have more examples along those lines, but I don't want to spend all my time talking about surveys. I will tell you a story. Now I'm going to talk about causal inference. I'll start with a story. Here, I'm going to share you another picture. I was contacted last year by some guys who work for Wikipedia. I don't know if they like are volunteers or whether they're paid, but like they do experiments to try to help people. Do you ever go on Wikipedia and it says, if you could just donate $3, it would make things so much better. So they do a lot of A/B testing on this. There's a lot of ways you could ask the question, right? And so they contacted me because they said they were doing some A/B tests and they got implausibly large estimates. And they had read some things I had written. It's so nice to know that people had read stuff I'd written. It's so gratifying. We work so hard, so it's nice to know that when complete strangers read our work. They had read stuff that I'd written about overestimates of effect sizes. And so they thought maybe I could help. And of course, it's Wikipedia, so I'll help them for free. So they had this story, and here there were, I'll show you the picture. They had the treatment was that these are pretty similar. That one's the treatment, one's the control. It's whether you have round corners or square corners on the box. So they're like, oh, this is silly, but it's free. Like people are already being randomly assigned to this. So it's free to do A/B testing. So they test everything, every stupid idea that comes up, because you never know, right? Like maybe there's something about the shape of the corner. Like, so they're like, don't hate on me, bro. Like we're doing this thing, but this is what we found. So what did they find? Well, the square corners was the treatment. It looks like if you go to the bottom right, okay, here at the bottom, the success rate is a percentage of people who clicked through and donated. It was 0.51%, which actually isn't that bad, right? What, 0.5% under the control, which was the round corners. When they tried the square corners, it went down to 0.43%. Well, that improvement was statistically significant. It was a 15% improvement decline. It was that treatment seemed to hurt by 15%. And the sample size is huge. And if you work it out, like I didn't trust them, so I did the calculation, and indeed, it really is like 80 zillion standard errors away from zero. Like you would not expect to see such a small change just by chance. So they wondered, like it seemed like too big. And in fact, like they said, yeah, we test a lot of different things, but we didn't really think this would occur just from chance, like p hacking or whatever. Like how many hypotheses do you have to test before you can get something that's like 12 standard errors away from zero or whatever it is? Like there's no way, it shouldn't happen. So where I was looking at this, and you all have perhaps been staring at this slide for a bit, and I noticed something about it, which maybe you noticed, which is that there's a treatment and there's a control. The number of trials, like, well, they're not close enough to equal. Like if you really give 2 million people this experiment, then you'd think it would be about 1 million each, not 108 1.08 million on one and 0.95. And that's another one you can easily test. It's like 80 trillion standard errors away from what it should be. Well, if this ratio had been 2 to 1, I'd say, or 3 to 1, I'd say, oh, that must have been their design. But it's too close to 50-50, right? Like it's close enough to 50-50 that it seems like the design is 50-50. So I said, I don't know what's going on. Like maybe you lost some data or whatever. So they said they would go and look into it. So this is what they found. So they had this is not the outcome of whether people donated, it was whether people are in the experiment at all. They had the number of people who got the treatment condition and the control condition as a function of time. It was a 12-hour experiment. So for a while it was working and then something screwed up. So here's a funny thing though, it's a funny thing about this story, which is that when I first saw this, my first reaction to them, I agreed. I said, this looks implausible. So my first thought was, well, is it possible that there's like big interactions? Like the treatment's really effective for some people than others, right? Like maybe I said, like, maybe you did the experiment at night and the treatment hurts at night, but helps in the daytime, like something like this. This is why I often say, when someone says, look, I see this effect and it seems large and statistically significant, I'll always say, well, I want to see like, you only did one experiment. Maybe in the future, it could be statistically significant in the other direction. So what they said to me was, no, we've looked at these kinds of things. The treatment effects don't seem to vary that much. They said it is true, like more people donate in the evening than the middle of the night, but they wouldn't see they don't think the treatment effect would vary. So then I remembered that because when you see, they said more people donate in the evening. So look, in the middle of the night, that's when more of the treatment was coming. In the evening, it was it was entirely like all have to do with the experiment being screwed up. Which is fine. They can do another Wikipedia experiment. It's basically free. But you could actually analyze these data correctly by just adjusting for time, and then it would probably work. It would probably just work just fine. Okay, so that's a silly example. But now let's talk about science studies and public health and economics and political science and psychology and so forth. Treatment effects vary, right? The treatments work for some people, not for others. I'll give you an example of that in a moment. But like obviously they do, because we talk about average treatment effects. So they vary. You wouldn't talk about the average if it didn't vary. When I was a student, when I was in graduate school, I took a class in causal inference, and they told me that if you have a randomized experiment, you don't need to, the people in your experiment don't need to be representative of the population, because if you have a randomized experiment, you get a kosher estimate of the treatment effect. But what they didn't tell me was that that's a kosher estimate of the treatment effect of the people in the experiment, or of the population for whom the people in the experiment represent. I mean, they did tell me that. They did say it's the average treatment effect of the people in the experiment. They didn't lie, but they didn't tell us the implication of that. So why didn't they? I'll get to that. But so I do first say that we've been bombarded with propaganda. No, it's not just that, like medical experiments, like, of course, like if they're going to do an experiment, like, oh, which form of open heart surgery works better? I don't think they should take a random sample of Americans and start giving them open heart surgery. Oh, no, didn't work on you. Yeah, I guess you would have died either way. Sorry about that. No, of course not, right? They do experiments on people, and medical experiments for ethical reasons, only on people who might benefit from the experiments. Beyond that, if you're doing a medical experiment, your number one, you probably think your treatment works. And so your number one goal should be, in some sense, to discover a statistically significant result. I mean, seriously, I'm not being cynical here. Like, really, you came up with a medical treatment, a new drug, whatever it is, you want to save lives. To save lives, you first have to convince people that it works. So let's set aside issues of like negative side effects and whatever, just efficacy here, right? So efficacy, like, yeah, so prove it. Like, so you should, for a medical experiment, you're almost morally obliged to do it on the people for whom you suspect the treatment will have the largest possible effect. which of course means you're kind of morally obliged to overestimate the treatment effect in any other population. So of course the true effect is going to be smaller. That's fine as long as we anticipate it. Unfortunately, we don't, it's not really that way. Like you see the published paper, just like my paper in 1994 didn't say this is the effect we found, but things might change in the future. So be vigilant. You only have one democracy, so don't break it. Similarly, when people come up with a medical experiment, they don't say, here's our treatment effect. And oh yeah, don't worry, it's an overestimate, because, well, even forgetting about selection on statistical significance, we did it on people who we thought it was really going to work for, because that's what we're doing. Like, that's the game. We should do that. They don't usually say that. Years ago, I wrote something for Slate magazine, and I mocked a certain study by saying that it was great that they're learning something about participants in internet surveys and college students. So, we eagerly await when they do it on the rest of us. And I got an angry email from a prominent psychology professor, no one who I've ever met, but he sent me, I guess, again, like strangers reading what you write. This time it wasn't so good. He said, complaining that subjects in an experiment were not randomly sampled is what freshmen do before they take their first psychology class. I hope you understand why that's an absurd criticism. And like, this actually made me think we do teach that and we shouldn't. It also made me coin the phrase freshman fallacy. The freshman fallacy is the fallacy of thinking that just because a freshman raises a point, that it's a bad point. So in this case, the freshmen were right and all the statistics teachers, including me, were wrong. We are interested in this generalization. Can I talk for 5 more minutes, or do I have to stop now?
I think you're good.
Okay.
We have until 5:30, so you can talk.
Well, of course, I won't talk till 5:30. That would be kind of rude, but I can talk for at least 2 more seconds. Okay, so now let me tell you a story where this came up. It's actually also an interesting story because it's a story where like I come across being a little bit clueless too. It starts it happened in March 2020. So put yourself back in that position when we didn't know how bad COVID was. Like, the hospitals in New Jersey were filling up, and we just like, it's kind of funny because if you were to put yourself back in March 2020 and say, well, hey, it'll kill 1 million Americans in the next couple of years, in some ways that would have sounded very alarmist. On the other hand, on a logarithmic scale, 1 million deaths is pretty bad. It's on the high end because we might have anticipated anywhere between 10,000 and 10 million. Or on the linear scale, I mean, I'm not the only one to have made this point. On the linear scale, 1 million's on the low end. Like, it's really not that bad. Like, yeah, a lot of people died. It's tragic, but 10 million, it would be just another level, right? I mean, I'm not trying to make any deep points here, but I'm just trying to put ourselves back in what it felt like in March 2020. It's just interesting to think, like, if someone had tapped you on the shoulder and told you it'll be 1 million, like, what would that mean? How would you think about it? It's an interesting thought experiment. But anyway, it seemed like this might just be filling up every hospital in the country soon. And we didn't know that they already had vaccines out there. And so it was like treatment. So I was contacted by somebody who knew somebody who was a doctor in New Jersey who was designing a trial for a drug that he thought could be effective for high-risk coronavirus patients. And I was contacted because the doctor had done a sample size calculation. He wanted to just, could I check it? So his assumption was that the drug increased survival rate by 25 percentage points. Like, maybe, I mean, these are high-risk people, remember, back March 2020, maybe their chance of dying would be 50% without the drug and only 25% with, so something like that. So under that assumption, if a sample size of 126 will give you 80% power, just it works out that because the effect size of 25 percentage points is 2.8 standard errors away from 0, which is what you want. So that was what he did, the calculation, and he had some number close to 126. And so was that okay? Well, yeah, he did the right calculation, but I thought, like I said, do you really think your drug is going to reduce, increase survival rate by 25 percentage points? And he said, oh yeah, he thinks 50 percentage points, but he thought he should use a conservative estimate because he's designing the study, right? So I said, so are you sure it works? He's like, no, I'm not sure it works. I could be wrong. I'm definitely not sure it works. That's why I'm doing the experiment. So I said, well, like, what if it was 10 percentage point increase in survival rate? That's still good. Like, I want to say like 1% percentage point increase in survival rate. I mean, 1% is great too, but for this kind of thing, like emergency, like maybe 1 percentage point is just not enough to be noticed, but 10 percentage points, that would be real, right? So he said, yeah, if it were 10 percentage points, sure. He would still think it's a good idea. So I said, well, maybe we should power your study to detect a 10 percentage point increase. He said, well, I really think it's 25%. Well, that was the end of our conversation. But then I wanted to kind of formalize this. So my statement was, if it could be 50, if the treatment effect could be 25%, it could be percentage points, it could be 10 percentage points. Now, how do I formalize that? Well, let's go back to the basics, okay? Let's suppose, just for example, that the survival rate is 30% among the patients who don't receive the new drug and 55% among the treatment group, right? So it increases survival rate from 30 to 55. So what that means is that, like, that's like saying there's 30% of people who are going to survive no matter what, 25 who would have died with the treatment, without the treatment, but the treatment saved, and then another 45% who would die either way. Well, not quite. I mean, it doesn't have to be. That's the simplest case. That's like the best case here, because it could be that it doesn't have to be that the treatment saves 25% of lives. It could be the treatment saves 35% of lives and then kills 10%. It's still net is 25%. That's actually better, because if you can figure out who are those 10% and not give it to them. But anyway, I'm giving you the simplest case. Here's my point, okay? In a population of 1,000 people, we have 300 people who would live either way, 450 who would die either way, and 250 whom the treatment works on, okay? But if you think about this, the entire treatment effect is entirely determined by how many of that third category of people is in the study. If you manage to go to a hospital where everybody is in this group of the treatment will save your lives, you'll have 100 percentage point increase in survival rate. Or if you're unfortunate not to have those people, well, it's not a characteristic of the person exactly, it's also the progress of the disease, right? Like if it's too early or too late, it might be. But the point is that, of course, if you think it's 25 percentage points, that means that you think that 25% of the people in your hospitals are of that type of person, or that's in that scenario. But of course, in that case, it could be lower, right? Because what if they start giving it to a bunch of people who are like, 15 seconds away from dying, right? Or what if they give it to a bunch of people who don't have, it turns out, had a very mild symptom, right? Like, it's so much going to be dependent on that. So of course you could get a 10% effect, but we tend to think of the treatment effect as this platonic quantity. What's the effect of the treatment? It's entirely dependent on who's there, right? So I mentioned this too. I was talking somewhere else. I think it was at Sloan Kettering, and someone commented on this. He remarked that, like, I was kind of wrong, and he was right that I was kind of wrong. So what I said is there are three kinds of people, and he said that's not really right. Like, he said that whether the treatment works is kind of a matter of luck, right? Like, a little bit. Like, it's some people the treatment might work. Like, so what if there are some people where the treatment has a 25% chance of saving their life? That's not the same. And I said, well, but can't you just imagine, like, this is how we teach, like in our textbooks, there's the potential outcome. So the potential outcome is you live or you die. So it's like they say, the great book of life has been written. We just haven't been privileged to read it yet, right? So each of us has a future life. All of our children have a long series of, future traumas ahead of them. We don't know what they're going to be, but like there's some distribution of them, but like it exists, right? So we always teach this, that there is a true treatment effect for each person. And he said, well, but would you say that, like, what if you told me that you're going to roll a die tomorrow? Would you say, like, like that there's a true, like you're either a 1, a 2, a 3, a 4, a 5, or a 6. It's a characteristic of you. So, well, no, that's random, right? So he had a good point that, so I think the potential outcome framework is a little glib. It's mathematically correct, but like as with all mathematical idealizations, there are places where it works better than others. So I think I was a little too quick, but I think my general point is still valid about if you can think of a 25 percentage point treatment effect, you could think of a 10 percentage point effect also. You just alter it to be a probabilistic effect. So I want to, can I speak for just a couple more minutes because I want to bring it together. Okay?
Sure.
Thank you. So the thing I want to close the loop. Okay, so I always say this, like when people, when students are writing papers or giving a talk or whatever, that if you do something, you say, well, I have this great idea, you have to explain, well, if it's such a great idea, why haven't people been doing it already, right? Like, and it might be, sometimes it's like, oh, technology, like we have faster computing power, we have a better algorithm, like nobody fit this model before because they weren't able to fit it, but now we can run it in Stan, right? Or we have new data, we have data that nobody had before. Or I talked to a sociologist and she explained why I should include this variable in my model, and so now we can do this. Like there's a reason, right? The reason, or, oh yeah, people have been doing it, but nobody noticed, right? Yeah, I found a paper from 1956, but then why weren't they doing it? Oh, because nobody could make money off of it, right? This is the standard example. Horse racing. The track skims 18% off the top. So you could have a great method for beating the racetrack, but if it can't beat the 18% VIG, it's still not going to do it. So a lot of things are like that. Like things make things better, but not enough better that they change practice. There's various reasons. Or like it's political, they wouldn't listen to me, whatever it is. But you don't want the default to be like, oh yeah, everybody else was an idiot and now we figured it out. Like that's not going to work, because like we're just people here, right? Especially not a talk like this where I'm trying to act like everything's so damn obvious all the time, right? That's the shtick. Like you could do it too, right? It's not like I'm saying that I'm some brilliant person who figured this out. I'm just saying, like, I'm a person who's willing to be disturbed by things. I think it's very important as a researcher to be willing to be disturbed and just say, this doesn't add up. This doesn't seem right. I'm bothered by this. The willingness to be bothered is important. So they give you tenure so you can get bothered whenever you feel like it, right? But then what is the missing piece? So the missing piece, I've said interactions are super important. Treatment effects vary, but yet in different ways, I've said people don't think about that. Why not? So why not? Here's why not. So let's imagine we want to do things right. So we're going to do a study. Maybe it's an A/B test because it's an experiment. We're trying to make money for somebody, or maybe it's a psychology experiment. Maybe it's a public health experiment where you're trying different treatments on different people, different participants. And you just listened to my talk and you said, well, I'm not going to do it wrong, so I'm going to have a pretest measurement. Well, that's great. And I'm going to allow the treatment effect to vary. I'm going to put an interaction in my model. It could vary by all sorts of things. I better put in a lot of interactions because I don't know. And then I'll post stratify. What's going to happen is my interactions are going to be very noisy, like, because the interactions are noisier than main effects. You can you can, like, how do I say, in interaction is like a different, so an interaction to first approximation has twice the variance when estimating, or square root of 2 times the standard error as the main effect. If an interaction is the same size as the main effect, would need 4 times the sample size. We talk about this in Regression and Other Stories. If an interaction is half the size of a main effect, which seems plausible, right? Then you'd need 16 times the sample size to identify an interaction. What does it mean to not identify something? Well, it's not statistically significant. Well, who cares? Well, it means sometimes it'll be negative when it should be positive. Like you're actually adjusting things backwards sometimes. So if we're in a model of statistics where what we do is we try to nail down little bits of near certainty, with statistical significance or the Bayesian equivalent, the high posterior probability, then that moves us away from including these things like interactions because they'll be highly uncertain. So you can really only do what I want you to do, what I want us to do, if you kind of loosen your grip a little bit and say, I'm willing to put things in my model that where the coefficient estimate will be noisy. And I think I need to do some regularization. Now that machine learning people have made statistics safe for regularization. So now we can do regularization all the time because like everybody knows that like deep nets do regularization. And so everyone's allowed to. By regularization, I mean use prior information to partially pool coefficients towards zero. You were already planning to fit them all without an interaction. And so how about put the interaction in, but give it a prior saying, well, I don't think this is gonna, I think it's unlikely it's gonna have the effect will vary by more than say 0.1 or 0.2. 0.2 is a lot, like increasing survival rate or decreasing it by 20%. But by putting some of these things in, we can at least begin to adjust. So that's part of it. And then part of it is being explicit about the goals. So it's moving beyond the idea that our statistical study is this little nugget of truth. Again, to get back to my story, which I had no idea I was going to talk about until the introduction came, that like instead of like we discovered this nugget of truth about redistricting, putting it in this population framework, that should just be assumed. Like it should always be just like if you don't have a randomized experiment, if you have an observational study, you have to explain why you think your comparison is reasonable. If you don't have a random sample, you have to explain why, blah, blah, blah. So in general, you like the generalization step should be kind of required. It should be one of the required sections of the JAMA paper or whatever. It should say the generalization to the population. That should be, how did you generalize? What were your assumptions there? That's as important as causal identification, external validity. So that's where I hope we are, or where I'd like to be. And I just, as I said, it's really been a pleasure to talk with you all. And I think that like, you can do this, like you're already there because you're already, I'm just trying to awaken the disturbance that you're already feeling every day when you write reports for people and every day when you say these things that you feel bad about saying. And so I think we together as a community can develop the tools and develop the expertise to do better and to better learn about public health. And yeah, let me stop here.
Thank you. That was terrific. I have a lot of questions, but I guess I should let the audience pose any questions. Sumana, are they going to be sending questions to you or to me?
I had a couple questions, so I'll answer right here. Just because I have one in.
You got questions.
Sure, yeah, and if I may just jump in, if anybody has questions, please direct them directly to Dr. Gelman or to Elizabeth.
Yep, so people send me a few. Jenny Horahan wrote, actually in direct mail, people have incredibly sophisticated information about how tiny changes affect response rates, a silver sticker on the envelope, etc. It would be interesting to see the literature on this. I'll say a couple things. First, my guess is that the estimates that you see are overestimates because of the selection bias that statistically significant effects get published, and those by definition have to exceed some size threshold. I do agree though, direct mail is like direct mail. You are talking about baselines in the 1% range. So you're talking about huge sample sizes and tiny effects. Like a tiny effect could be important, right? That's so I agree with your point that like the Wikipedia people aren't stupid to test all these A/B tests. Like some things can matter, little things can make a difference. Why not? There's no way that I think it's highly unlikely that round corner thing would have that huge effect. They also have a certain amount of experience in what works and what doesn't also. But certainly they should try these things. Go for it. Should I just keep answering questions here? Go through.
Yeah.
Jia Cheng Chen says you often discuss bad or ridiculous research on your blog, which is selection bias. It's just what people send me, you know, like, would you be open to occasionally commenting on good applied research you come across? I do. Maybe I just need to flag it more. Like, I do sometimes talk about stuff I like, and maybe just people don't notice, but there's a lot of stuff that I like. Actually, somebody asked me about this just yesterday. Like, can you name some paper you like? And I thought, well, I don't want to mention something like from one of my friends, you know, like there's great research, like I just think is wonderful that my friends do. So I went to I Googled APSR, the American Political Science Review, and I went to the APSR page and I clicked on their recent papers, and they all look good to me. No, they weren't perfect. Like, somehow nothing is quite how I would do it. Like I always like to have more scatter plots, like see more of the data, like, you know, this generalization stuff, but I thought they're all reasonable. And so I guess there is some selection bias. Like, sometimes it's partly that the things that get the most attention can often be the worst. Also, sometimes you have a paper which is kind of fine, except how it got reported, right? So some people I know at Teachers College at Columbia did a study recently. It was part of they had a little module in a study where an experiment where some low income mothers were given cash payments, and then they're trying to see how things work after that. And they had some measure of they did they measured electrical activity in the brains of the children, that like 1-year-olds actually. But I mean, they just put some cap on their head. They're not like hurting the little kids. And they found there was more high frequency brain activity among the treated group than the control group. Well, yeah, but it's super noisy. If you look at the data, like, there's a huge overlap between the treated and the control group. So I wrote, like, I don't buy it, but like, I think it was actually a good paper. Like, I think that just like I think they should have had a graph showing all the data, and that would have been clear that any effect is very small compared to the variation. And I think like they were sort of careful. They maybe should have been a little more careful, but like, it's just that it got reported in a certain way. So if that had been sitting there in the APSR or whatever without the news headlines, I would have said, oh, this looks interesting. Yeah, like, this is good. They even say like our results are not statistically significant, but they're suggestive. Like, what I would have said is, I like this paper. But like, yeah, they should have done a few things, but I like it's good research. Their data are all available. So a lot of things are like that. It's like which end you take it from. So you could just say like, I'm a negative person because I focus on the bad things, or like starting with when something gets hyped, then it's natural to kind of want to deflate it. There's some very interesting discourse questions and interesting selection bias questions about what gets reported. Somebody should try to look into it. Rebecca Zimba says, with regard to medical experiments, wouldn't be enough to show non-inferiority if the new treatment would be less expensive? I mean, it depends. Yeah, in some contexts, you need non-inferiority. I think you all probably know more about this than I do. I mean, I think that there are contexts yeah. Can you mute this thing?
Can you mute yourself?
Can you do it? You have the power to mute people, I believe.
Ilana, can you?
The host does. It's okay. Got it.
Okay, thank you. Yeah. So I think it's silly for me to be talking about this. I don't know anything about medical experiments, so let me not waste your time on that. Just because it's a good question, but I'm not the expert. Isaac Michael says, in associative modeling of public health and healthcare data, do you think there tend to be diminishing returns of accuracy from marginal increases in model complexity? So I guess the point being that at some point, like, you start adjusting for more and more things, and you lose control of your model. I think that is an issue. I mean, so there is this thing, like, sometimes people have like, there's the like machine learning approach, like how they built machine to play ping pong and stuff like that, where you have like trillions of data points, and you run this auto regularized regression. Like, it's super cool. It won't necessarily work so well if we have a study with like 150 people in them. So I think sometimes we have to like a certain amount of like teamwork and pre-processing would be needed, that there are like, so the machine learning people can do some analysis on these crappy like medical records data and figure stuff out, and then maybe that can be summarized in some way, and then we do kind of more small sample type methods like on a public health study that has fewer people. I do think there is, I mean, I think there's a big thing here. This is something that Beth Tipton, the statistician and education researcher at Northwestern, has talked about a bit, which is there's a kind of gap. There's a gap between a little experiment and the big real world. So like we do these experiments with 300 people, like in social work, right? Like it's hard to get 300 people in a study, right? You get 300 people and you demonstrate an effect, and that's supposed to affect policy, but like your estimate's super noisy, and like, or else you have like the real world where you got millions of people living their lives. And it seems like we should be able to incorporate kind of learning in the real world, but observational data are so crappy. So like people have talked about this, like just a little bit of experimentation within the observational world maybe could help. But I don't think we're there yet. Like we do have people like economists and others who do these like large randomized experiments where it's a multi-center thing, and thousands of people in the study. Various people are like flipping coins all over the world and so forth. But that's still not enough. I think there has to be some more of a true integration, like basically say we're doing observational analysis, but getting certain benefits out of the experimental idea. And I think the key concept of experimentation is that you're experimenting, assigning treatments, not randomization. I mean, randomization is fine, but you can do a lot, like the act of treatment assignment, the idea that there is a space where it's happening seems to me to be important. Oh, okay. Jalai Osman asks, do you think the lack of effect in your data from two truths and a lie may be related to the nature of the statements that people are willing to expose? Perhaps the statements were all uniformly uninteresting. Oh, it could be. I mean, I just think I did it near the beginning of the semester. I just think it's a great activity because students get to introduce it. Really, I just wanted an excuse to have them introduce themselves to each other. But then I just think like it's a crime. Like I can't do that. I'm not going to say like, I'm not going to go into class and say, look, spend 5 minutes introducing yourselves to each other. That's a waste of class time. That's an insult, right, to the students who've paid tuition and so forth. So I had to, but it's not a bad message, right? Like it worked out. Like no effect, that's interesting. You don't usually see examples of no effect in the textbook. Well, like it was kind of, you can't lose with an example. The other example I do is I do item response analysis on their final exam scores, which is another great logistic regression example. I write multiple choice exams because I just think they're more fair and they take more work, but they're fine. Anyway, you can do the item response analysis and just compute total score for something simple, even not a big hierarchical model, but just compute a total score for each student. And then you can just make a plot or a logistic regression of whether they got the question right on that. So I did that. And there are some questions where the discrimination looked like it was 0 or negative. Like most of the questions pretty clear. The students who do better in the test do better on the particular exam. In this case, it was a 24 question exam. And so there's a lot of data there. And I had like 35 students. So, well, a couple of the questions were like the students, like there was no relationship. So I looked, it turned out, well, one of them really was no relationship, but the others I had messed up. Like I had typed the wrong thing into the answer key. And so so that was a great lesson too. So of course, like, great, research gives great lessons, but also lessons gives great research, right? It goes both ways. We're so fortunate to be able to teach these wonderful students that we have. Oh, looks like that's all the questions you have, but you can ask more if you want.
Well, I had a question for you about this idea of weighting to populations. And in your example, you were talking about sort of convenient sample, but then asking the people in your sample a bunch of questions to kind of get at like the distribution of characteristics that might make them more likely to be in your sample versus not in your sample, and then trying to take that into account in order to get a more of a population estimate. And so you're basically saying you're going to weight your sample, right, based on assumptions? No?
Now I'm weighting my sample. So it's 2 stages. First stage is I use my sample to fit a model, which will give me predicted outcomes given their characteristics. Second, I post-stratify by applying that to the population. So, I mean, I know what you're saying, and there are situations where, like, I know why people say it's weighting, and there are situations where it's the same as weighting the sample, but strictly speaking, I'm using the sample to estimate a model, and then I'm weighting the model inferences. So I'm doing it, I'm doing a division of labor, sort of comparable to how when we talk about decision analysis, you might say, first I'm estimating probabilities, then I'm going to pipe them into the decision analysis. It's kind of like that. But there is a challenge that we don't know these things. We call them nonsensus variables. So it sounds like nonsensical, but I just think you have to make assumptions about the nonsensus variables, and that's just for reals, like needs to be done. But better to make the assumption explicitly than implicitly.
Okay, and then you don't think it's worth waiting on, distribution of characteristics that in the population, like, if you use the New York City Department of Health data,
no,
they give weights to
definitely. Oh no, I would also, I would the idea would be that you'd post stratify on the full table of everything. So yeah, certainly age and sex and socioeconomic, so forth. Now in practice, that would imply knowing a post stratification table to a level of detail that you wouldn't realistically really know, and so it implies that we cut corners in various ways, but conceptually, yes, I would adjust for all those things too.
Good, because that's what I make my students do. So
well, we talk about it in chapter 17 of Regression and Other Stories.
Yeah, great.
We have a chapter called Post-Stratification and Missing Data Imputation, which I just love. I just love that post-stratification gets its own chapter because
Terrific. Does anyone have any last? We've got like 10 minutes left. If anyone has a couple more questions.
I have another one. Here's a question. Larry Lutsky asks, if you find significant differences between subjects randomly assigned to treatment and control groups, do you need to control for them in the analysis? So first, I'm going to be really picky and say, a few years ago, I stopped saying control for unless I'm really controlling for things. So for example, I would say adjust for. So for example, if I'm doing a lab experiment, controlling for temperature means I actually set the temperature in the room. Controlling for temperature. Adjusting for temperature means like I have data and I adjust. So yes, you do need to adjust for them in the analysis. Well, do you need to? You don't need to do anything, but you should. Yeah, you should. Because you could say, well, I don't need to because my estimate's still kosher, because it's randomly assigned. So I don't need to. So it depends on the context, right? If you have precision to burn, then sure, who cares, right? But if you don't have precision to burn and you are your standard error is kind of large, then yeah, you want to make use of as much information as you can, I would say.
But can I just add a secondary question? With randomization, the assumption is that you're equally distributing all the confounders on average, so there's no confounding effect. And then if you adjust for one, that might create a confounding effect because of an unknown confounder that you didn't assess. So sometimes I'm not really sure.
Well, I think that okay, if it's randomized and nobody dropped out and anything like that, then any of these estimates are fine, like statistically kosher, right? So like they're all a bunch of different unbiased estimates. Well, they're not literally unbiased because you're estimating the regression coefficient, but they're close enough, right? So like in that sense, like so for a randomized study, it's safe to adjust for stuff. Adjusting for stuff won't introduce a bias in that sense. Of course, the adjusted estimate could be worse. I mean, I think in expectation, the adjusted estimate's better, but it could be farther from the truth because things are kind of random. I do recommend, or I recommend is maybe I would like to be able to recommend that when you do these adjustments, you do put in priors, you partially pool these adjustment factors. So like you don't need to just adjust it using least squares. Like what if if you adjust for 50 variables using least squares, you can get a lot of noise. And in fact, that kind of happened with this study I mentioned of that they did at Teachers College, that I think it was a mistake for them to adjust for so many things uncontrolled. But yeah, anyway, so then the other thing is, yeah, if it's an observational study, it is true that adjusting for things can induce a bias, but of course, not adjusting can also. I still think it's typically better to adjust. Like I know the thing that people say about there are cases where the adjustment can introduce a bias, but that somehow only really matters if you know that ahead of time, which I don't think you would know. Oh, a couple more. Jiaqi Zhu says, can you explain more about the difference between adjustment, propensity score matching, and post-stratification? You should get Jennifer to speak. Just, she'll tell you about all this stuff. She's the expert. Yeah, I mean, that we get into that in our book, but it's just too much for me to talk about here. Leon Di Stefano says, you argue that 1, interactions are real and important. 2, we should model them by including the a priori assumption that they're small. Good point, Leon. As he says, there seems to be a tension here that on one hand, I'm telling you interactions are important, so put them in. And on the other hand, I'm telling you, yeah, but it's so hard to estimate them that you better partially pool them. So let me amend what I said and say that you should partially pool them toward your model. And your model might be 0, but maybe it shouldn't be 0. And it should be kind of explicit. So if our model, that is, so there are situations where like additivity or approximate additivity is a reasonable model, right? So it's a lot of situations where it'd say, here's the treatment effect, and I have no real reason to think interactions will be large, nor do I expect they're going to be in one direction or another. So sure, right? On the other hand, what about that hypothetical medical study I told you that's like every study that's done, where you're really purposely trying to aim for the people for whom the treatment is most effective? So you can't, if you think about that as a design problem, you have an x-axis, which is like some measure of health or something. And let's just say you're really trying to get people in the middle of the range, because if they're on the high end of the range, I did that right. If they're in the high end of the range, then their treatment's not going to work because they're already dying. If they're the low end, it's not going to work, and whatever. So it's in the middle. So then you do your study, you get lots of people in the middle of the range. You have like no leverage to estimate that interaction, but it's important. So there, I think you need theory. Like you need to say, like sometimes you can let the math be your theoretician. Like you embed it in a logit model. And so in a logit model, like the probability is near 50%, the effect's bigger. Otherwise, sometimes you have to do more. But I do think you're right. I think that you made a very good point. That like, yeah, like it's not that I'm saying interactions are necessary. I think you need to put in priors to realistically, and I think sometimes the priors are that they're small and you want to be able to make the adjustments that you can. Other times the priors are that they might be large, and then you'd want to put that in your model too.
All right, was that the last question you have?
Yeah, well, thanks for the opportunity to speak with you all. I just feel bad that we couldn't all be in a room together coughing on each other like a normal year where we just give each other a few colds, and that would be that.
We'll invite you back when we can do that.
Yeah, exactly.
Thank you very much. I hope everyone enjoyed the talk, and Dr. Gelman, thank you so much for joining us. It was fascinating.
Okay, bye.
Take care.